So yeah, come in, come in. So if you are, now to prevent this, if you are feeling sick, right? If you are feeling sick, then what are you to do? Don't come to class. Send me an email and either ask me for the Zoom link so you can attend virtually, or just catch up on the lecture later. That's no problem. Most of my lectures, again, will be about 10 to 15 minutes of me either rambling or doing some programming in class. Otherwise, the time is devoted for you to work on your work. Now, if you are here and you lack a laptop for some reason, which happened in the morning, that's perfectly fine. I know not everybody can have a laptop or afford a laptop. There's a kiosk right at the bottom of the stairs on the first floor. Swipe your OWL card, receive laptop. Done, right? That is so there's a laptop kiosk if you need a laptop to borrow. Otherwise, there are lots of people around here who I'm sure would be more than happy to collaborate with someone on problems, which you're more than welcome to do. You are more than welcome to work together. And if that's a complication, you know, just type in the comments that you're working with somebody. So regardless, it's not going to be a huge issue. All right, now let's go ahead and cover. Now, yes, this laptop, this current week, I'm sure, at least these first couple of days are going to, it certainly feels unreal to be back in class and in person, doesn't it? Like everything is just like kind of like a dream, and not in the, oh, I couldn't dream of this day coming. It was more of a, like, it's just unreal, right? Because so fortunately today, this week's stuff is good for that. Now, first off, if you need more time on the array list exercises, let me know, and I can grant an extension. I can alter the due date for everybody. Do people think they need a couple more days on the array list or no? Yes, a couple nods. Okay. Let me go ahead and alter the due dates for this. Right. Normally I don't need to, but I do know that that it has been a very hectic day. So I'll move it to the 27th, save and notify the users that this has changed, yada, yada, yada. Okay, now for this one, we'll see where we need to go with this. I'll post, with these ones, they'll have to move. So I'll discuss those module 4 exercises. You don't have 2 homework assignments. You have the choice of one, you have the choice of 2. In other words, you do one or the other. One is easier than the other, but if you do the other, you'll get some extra credit. Okay, so you have that choice, but they both work off the same code. Again, more detail on that later. So this one is, but this week's homework is more like a math worksheet than anything else that you've seen before. So, and what I mean by that, this is it. Now, ignore the 5016. That is for the online graduate course that is based on this course. So last time I did it, it was for my graduate class, but don't be afraid of that. That graduate class is based on the undergraduate class. So long. Anyway, so here I've created a math worksheet. All right. Now I'll go through this in a bit, but you'll see, but first, out of 100 points. Now, I don't find the whole way that typically happens for math to be too useful, which is you complete homework, you turn it in, and then you get it back and it's like, 87. Okay, that's not very useful, just receiving a numeric grade back. Now, what you're going to do is you're going to demo this like any other assignment. You're going to come over to me and I'm going to say, these look fine, but this one and this one is wrong. Go back and fix those. So you should be able to get full credit on these because I will tell you what's wrong and tell you, if you need to, I can tell you how to fix it. All right. So let's see. So we're going to be dealing with big O notation. Now, some of you may have had exposure to big O notation. Some of you may, in fact, just had a class today that talked about big O, if you took discrete math too. If you're taking about, now, those mathematics courses are based on mathematics courses. Those come at it at a more theoretical point of view. We are not doing this theoretical. We are going with a more practical and sort of scientific way. We are not trying to figure out what the runtimes are by proving it. We are trying to figure out what the runtimes are for our programs by observing it, and we're building up a working vocabulary for it. Because pretty much every algorithm we are dealing with in this class falls under one of 5 different runtimes. And for this, and for the first part of the class, we're only dealing with 3: linear, quadratic, and constant. Those are the 3 runtimes that we'll be dealing with primarily. Now we'll be mentioning some others, but for the most part, everything we deal with lists is going to be either constant, linear, or quadratic. Okay. So first I'm going to be asking you given a T of n, which is the typical way we write the T being the amount of time this algorithm takes, given an input size of n. What is the big O time complexity? And big O follows some rules. Again, watch the videos on it. But what big O means is that it means that the time is never going to be worse than a function that's shaped like this. So we can add in some number and multiply this by a factor, but the curve is never going to be any worse than this. Right? It's never going to grow any faster than something that's n cubed shaped or n squared shaped or whatever. That's what it means. It's never going to be worse than. It's an upper bounds. Okay. There are other terms that mathematicians use, like big theta and big omega, and we don't really use those too much. We'll cover them later, but we don't really use them too much in computer science. We almost always use big O because Murphy has it out for us. Murphy and his law. Okay. So here we're going to basically, I want you to simplify these things. And you do that, well, we're using the instructions I give you at the front of the page, which is that you only deal with the thing with the biggest degree, and you don't care about the factor, the factor that's attached to it. Now 3 and 4 are trick questions. I will go over the proofs of them either at the beginning of next class or the end of this class, depending. So 3 and 4 are trick questions. They are converging series, meaning they converge. There's the formula. So I highly recommend not going with your first instinct and instead looking up the formula by like typing in 1 + 2 + 3 plus n, and figuring out what that comes down to. This one's extremely fun and extremely weird, especially if you let it go to infinity. Otherwise, you'll have to look at logarithms, but basically what we care about is the behavior of this time as n gets large, and I mean large. Let's say 10 to the 1000th power, kind of large, right? Let's go ahead and just using problem 7 as an example, right? The idea here is for big O runtimes, and annotate, for big O runtimes, if we let n be equal to 10 to the 1000th power, right? If we plug that into here, we're looking at 10 to the 1000th plus 10 to the log of 10 to the 1000th, which is just what? 1000, right? Logs aren't too scary. They're just made to be scary because your math professors don't always, or high school math teachers don't always know the best way to describe them. But in the end of the day, this is essentially so small that it's an error, right? It's smaller than error would be in encoding this. This 10 to the 1000th is bigger than our puny 8 brains can comprehend. Okay, so that's what we're looking at. What happened? So at what? And that's why we only care about the largest thing. That would make this answer O of n. So this next one asks us about operations of array lists. This one corresponds to the very last page because my rendering was bad. This is a page from one of my favorite books that I had as a kid. It's still one of my favorite books, which is a book of maps and maze puzzles. So these questions ask about that. So 18 is poorly phrased in the sense that it's ambiguous. So and so there are multiple valid interpretations of number 18. I don't really care which one you use, okay? So just FYI. Finally, this page deals with an algorithm analysis of Bogo sort. Now, what is Bogo sort? Bogo sort is a sorting algorithm that only exists in the context of class like these. Bogo sort says, I want to sort a deck of cards. How should I do it? Well, I will throw the deck up into the air, let the cards fall willy-nilly, pick up all the cards, and then check if it's sorted. So it is sorting a la 52 card pickup. And I'll just keep doing it until I get it right. This is obviously a very terrible way of doing this, but it's great for, just kind of doing algorithm analysis and understanding, how slow certain techniques can be. So there is one other algorithm that exists purely for pedagogical purposes, which is Stooge Sort, where I believe you sort the first 2/3 of the list. You stooge sort the first 2/3 of the list, you stooge sort the second 2/3 of the list, and then you stooge sort the first 2/3 of the list again. Kind of like that slapstick routine the Stooge brothers would do, where they slap each other. So but that one's more for the 3223 kind of class. We look at Bogo sort here because the algorithm analysis doesn't require us to actually like go through and prove mathematically what it is. We can kind of just work out via kind of thinking about decks of cards, how long this would take. Finally, the last point for this is for each of the methods you wrote in lab 2, figure out the time complexity of the method you wrote in. Now, this part was more applicable for when it was turned in physically, but honestly, don't turn it in physically. Just don't. I don't care how you turn this in. I don't care if you write down the answers on a piece of paper and just the answers and just then take pictures of that and upload that. That's perfectly valid. You can download this PDF and just write on top of the PDF. Sure, you can convert it to a Word document and save it and submit it. Basically, the only time I'll accept the Word document as a submission. Really, I don't care how you submit it electronically, just as long as there's a record. Do it the way that's easiest for you. If you want to, once I'm done talking, if you want to take a minute to like leave the room so you can go over there, and I think there's a printer over there that you can use. If you want to go and print out the paper because you work much better on paper, go ahead, go for it, right? So really, I don't care. Just as long as it works for you. That's what I care about, okay? But essentially just, again, turn it in. You'll demo it to me anyway, so I'll be seeing your answers. Again, this is just for a paper trail. It's much more important on campus because sometimes my Wi-Fi just goes bleh, and the grade doesn't upload properly. So yeah, you can start this before you finish lab 2 if you wanted to, but for the last part, you'll need to do lab 2. And again, I'll work with, if you're not sure about your answers, make a best guess and then come over and we can discuss it, because your answers, because let me tell you, your answers are either going to be constant time, linear time, or quadratic time for each of the functions you wrote. You most likely didn't mess it up so bad that you were cubic time or anything like that, n to the third. Now, later on in the semester, we'll be dealing with log time and log linear time. So O of log n and O of n log n. Log n is when we do stuff like binary search, where basically the search space gets cut in half every single time we take a step. And then log linear is for stuff like quick sort or merge sort, where we do a divide and conquer approach. Again, for these, we don't do a rigorous mathematical analysis. There's other classes for this. This is more of a, can we look at this, understand how the program flow breaks down, and just kind of build up a good intuitive grasp of the runtime. So it's okay if you're, in other words, have trouble with it now, but that's fine. I will now, again, for 3 and 4, be sure to look up the formulas for those. I think the beginning of next class, what I'll do is I will basically both prove, I will quote unquote prove it, because it's not actually proof, by kind of drawing it out for you. I will show it to you I will reason it for you graphically, but I will also formally prove it to you using proof by induction, which is important because proof by induction and recursion kind of go hand in hand. There's no recursion involved in this, but ensuring that your recursive functions work involves the same kind of thought process as proof by induction. If you could just pull up your map. Yeah, sorry. Okay, so that is that. So how does the rest of the day work? Well, if you're ready to demo, you can come up and demo. If you want me to, if you have a question for me, I can answer questions, you know, but basically the time is like it was in online. This time is, I try to give as much time of it for you to work on this and ask me questions when you encounter difficulty. Okay, so any questions before we get started? All right, so you're good to go for work. And again, if you want to step out of the room to go and print the document and come back, that's great. If you want a demo, just make your way up here or raise your hand and I can, if you've got a question. And I see we have some people online. Anything from the peanut gallery? Sorry. Any questions? Okay. I will keep the Zoom on. I'll keep the Zoom on. If you've got something, drop it in chat and I'll see it. Or, you know, just start yelling from the computer and I'll come over. All right. Yes, come over.
I just wanted to know if there's